In this tutorial, I will introduce QSAED3, a computer software for quantification and processing of SAED patterns. The current version is 3D. This is one of the main components in the Landyne software suite for electron diffraction simulation and crystallography analysis. You may download the software suite from the website on the screen. We already showed the installation of Landyne suite together with the Java runtime environment and the Java advanced image in the first video of the series. You can find it on YouTube by searching for Landyne plus Launcher. Please refer to that video to install the Landyne suite on your PC. The higher the resolution of the monitor, the better to run the software. My laptop has displayed the resolution of 1920 x 1080. Here is the Landyne launcher icon. Double-click this icon to activate the launcher. If you have a license file, please copy the license file to C folder, Landyne 3 program. Here is QSAED3, and here is the license key. Click this button to start the QSAED3. A license dialog will pop out in case you don't have the license file. Then you should select the demo mode to continue. Let me briefly introduce the functions on the menu bar first, and then go to detail with example later. File. Load electron diffraction pattern. Save HKL date. Save display as a JPEG. Save display as TIFF. Exit. Process. Calibrate scaling factor, which is used to measure the basic vector or the length between the diffraction spots. Shift and center. Move the incident beam to the display center. Resize and rotate image for image processing. Invert image grayscale. Turn black background to white background. This one adjusts possible leftover edge grayscale. The last one will erase the image. Quantify. First one is a digital viewer. If there are intensity here, this will show the actual density distribution. Beam stopper. If your diffraction pattern have a beam stopper, we'll use this one to simulate the situation. (2D) pattern. This is main function for the QSAED to retrieve the intensity. (1D) profile. This is another function to retrieve the intensity, mainly get the length of between two diffraction spots. The last one shows information of basic vector. Pattern. The color will show the pattern, the retrieved intensity. Adjustment for you to restore the true symmetry of the pattern. Preference to show what you want to show on the screen. ROI and TIFF control the size and the resolution of the output. The font will control the size and also the color of indices and the style. There are 3 styles to choose. Option to hide the toolbar or show the toolbar. Look and feel, there are 3 choices here. Help input current drive and SN and version. Current drive will show the serial number of your hard drive. You can copy this number or take snapshot of the dialog sent to us so we can prepare the license key for you. The current version is 3D. There are 2 ways to load image in QSAED. First, use standard window file system. Go to File, Load Image. This is in QSAED. Take this one, open. Image show up. Let's clean the image. The second way is find the image and drag and drop to this drop box. Go to C folder, Landyne 3, Experiment, QSAED sample. This image, click your mouse left button and drag here and see the move. Release it. That is exactly the image we loaded before. The first application of QSAED is to process the experimental electron diffraction pattern for publication. The experimental SAED pattern rarely used directly from experiment. Usually the pattern will cut to square with the incident beam in the center, and also sometimes it's need enlarge and rotate to make the pattern look nice. It takes time for the procedure, especially for many of this diffraction pattern to process in the same time. QSAED3 simplify the process for both SAED sports pattern and rim patterns. This is the incident beam. We need to move this point to the center of the display area. First, click this button. Choose this point and hold mouse left button. Move mouse point here and release. It's very simple to find the center of the diffraction pattern. The guideline can be changed with the circle. I put 8 here or 6 here. To guide your patterns, you can show the guideline only or the circle only. If you make mistake, move your pattern too far away, you can use the undo shift to bring it back. To resize and rotate, just drag this slide bar, but you need remove your pattern center back to here. To rotate, we want to make a guideline here, so we may choose 8. Either slide this or use number here. And now see the vertical line is parallel to this vertical line. Readjust the beam center. The pattern is aligned and resized and rotate. We are ready to output this pattern. You may like the background in white, so you can do process, so you have the pattern contrast inverted. If the original image are small, you may have edge left over in other color. For example, like this size. So you can use the adjust edge contrast in such a case. Just slide this bar to so it make look like the same image here. Let's bring it back. bring this back. The last step to save the image, get a nicer pattern for publication, is to define the size and the resolution. Click here, it shows this square, inside this square will be saved. And this is for teeth PPI, point per inch. Default is 300. Usually the publication require 300 or up. Let's change the size to 500. Immediately the size changes. You can define how large it is. Now go to File, Save Teeth Image. You can change the name here and go to Save. Your image is saved. The saved image is in C folder, Landyne 3, Result, Demo QSAED, this file. Instead of adjust the brightness and contrast to enhance the patterns, we will remove the background of the pattern and retrieve the intensity of diffraction spots. The intensity of diffraction spots are expressed in the radiuses of circles. As an option, true symmetry can be restored in the processed electron diffraction pattern. The next main application is to measure the intensity and basic diffraction vector. The shift we introduced before is mainly for prepare the select area diffraction pattern for publication. It didn't need exactly to be the center of the display area for measure the basic vector. We need to calibrate the scaling factor for measure the reciprocal lattice. This can be done by shifting the scaling bar to the center. So when end is in the center, then we can show the matching circle. And get rid of the guide circles. Then we can adjust the other end to measure the radius. Then we just fill this number. Here is 5 1/nanometer. Select this to 1/nanometer. Put here to 5. After this, we can bring the diffraction pattern back. Now let's find out the two-dimensional basic diffraction vector. Go to 2D pattern. If you first time use the software, you can bring the hint and tips by check out this. After a while, you can not show this up. Let's check this out. First, find 3 spots in 2-dimensional. Give any index. The default is 10, 01, and -10. Check this one is you can use the magnifier help you to find the most intensity spot. This will be the one, and this will be the 2, and this will be -10, the third one. So you define the 3 refraction here, then you can go to search. Before you search, you can define how large area of the diffraction you want to search. So let's check. I show you a hint. Says adjust the range and the radius to refraction to create circles before making refinement. Okay. We make this too big, so we'll adjust this one and this one. For refinement, we just use in the first ring and the second ring, and see all the spots in the circle. We can make the refinement. You may try several times for the refinement until it's stable. Click the refinement buttons a few times and result should be stable. Otherwise, search it again. This defines the basic vectors. And next, we're going to find the background. Smoothing, prepare the background. calculate the background date, it may take for a few minutes. This is the background. This is the peak. The red one is the background. So it's okay. Before we retrieve the intensity and the basic diffraction vector, we show you a tool called the digital viewer. This is a magnifier to show the local. You move your mouse to anywhere, it shows the local, actually digital information. In this way, you can tell which diffraction spot is saturated or not, and also help you to find the true spot location. Let me introduce the function in pattern. The first one, we can choose any color to represent retrieve the intensity. Default is red, now it's in the pink. You can also choose the blue. So you got this blue. Let's return back to the red one. Next one is for the adjustment. The first one adjustment is to adjust the overall scaling factor for the whole intensity. Some of the circles are overlapped, so let's reduce this one a little bit. This will not change the original date we retrieved, only for display purpose. We'll show the rest of it later. Let's go to Performance. Here we can choose the sound on or off during the process. We can show the three, choose the refraction, 1, 2, 3, on or off. Let me first to remove the experimental pattern. We want to show, we'll make it clear. So the three spot, you don't want to them appear here, so you can turn it off. You can show the basic diffraction vector on or off. You can put the central beam on, marked with a cross. You can turn the intensity to solid, so make them more revealing. You can choose only show the diffraction patterns without retrieved image by making the swap. We need to define the resolution first, before retrieving diffraction intensities. Two methods are designed for unsaturated and saturated patterns, respectively. In the first case, Diffraction intensity is simply sum of the pixel intensity in each circle. In the second case, Gaussian bell-shape function is used to restore the peak shape. Diffraction intensity is then calculated from the Gaussian function to compensate the cutoff due to saturation. The background intensity is removed from the same curve in both cases. Diffraction intensity is retrieved for display and can also be saved to HKL intensity file. In our case, we have a kind of saturation. This is the first method, retrieved intensity. Select second one. The second way, we'll use the second way, retrieve intensity here. Let's go back to intensity adjustment. There are several choices here for you to deal in different situations. First one is as it is, you retrieve intensity. The second one is for you to restore the lost diffraction if you use a beam stop here. And the rest three deal with different symmetry. This one is 2-fold symmetry, this one is 4-fold symmetry, and this one is 6-fold symmetry. If we believe our pattern has a true 2-fold symmetry, we should use this one. And see here the diffraction pattern show you modified, restore the true 2-fold symmetry. This is look like a 6-fold. If you believe it should be a 6-fold symmetry, you may choose this one. It will change your pattern truly 6-fold. But our pattern is actually 2-fold, so we choose this one. To retrieve the intensity, we use the two-dimensional index system that just uses two short vectors in this pattern. The true index should be converted, use the relation here. You can define the 1, 0 as a true index here. And 0, 1 a true index here. Then you do the transformation, click here. You get the HKL intensity file with a true index there. Then you can save here HKL intensity. Depend on you choose either original retrieve the date or process the date. Save here the current intensity. We get the intensity distribution. The same time we get the basic diffraction vectors. We have the scale bar labeled as a 5 1/nanometer. It measured 70.0 pixels. The basic vector 1 pixel 24.8, vector 2 is 24.5, and this is converted to 1/nanometers. See, these two factors are slightly different, and the angle between them is 58.79. It's not the 60 degree, that's why we said it's pseudo hexagonal, but it's not really 6-fold symmetry. The retrieved diffraction intensity can be used to replace the Fourier intensity of a high-resolution image. Those get an enhanced high-resolution image. This software will add to Landyne software suite soon. Let's return back to the experimental image. The third application is line profile for both periodic or non-periodic lattice. This is for a quick measured reciprocal spacing, which can be used in another software called Resize 3 for unit cell determination. To measure the linear profile, we selected quantify one-dimensional profile. We select one line of the diffraction pattern. Start point here, end point here, and you can see from this line start point, end point 2, the profile is like this. We can show the intensity or spacing here, show the steps, and then we can adjust step and 1/10 or 0.1 steps here to make all the vertical line fit to the peak positions. Try this. This is perfect fitting now, so all lines are fitting to the lines, and we can read this one is 24.0. That means along this line, the pixel between the diffraction path is 24. If this is non-periodic, we can also measure the profile distributions. We can show the profile in different colors. If you hold mouse left button, and you can move the profile to the center. And you drag down, you can adjust the whole overall height of the peaks. If we choose another line, we start first point here, and the point here. And you can see the same thing happen here. So this is measurement for the profile. Thank you for watching. Please check our other videos about Landyne software suite for electron diffraction simulation and crystallographic analysis.